All right, so to continue our 9-1 notes, what we talked about was that, and you can kind of see it with symmetry, like if I draw in this auxiliary line, do you see that that top triangle will fold right down onto this bottom one? They are actually congruent because of this shared edge, because of the all radii are congruent, and because of the 90-degree angle. We can actually prove that they're congruent by HL. I'm not going to make you do that proof, but what's important here is that you then recognize that this will equal that. Tammy?
What was the theorem before that?
The theorem before this, was it this one, I think?
Yeah.
That says tangents from a common external point are always congruent. Tangents from a common external point are always congruent. And so this whole page does that proof by proving these triangles congruent with HL, and then using CPCTC to prove that those pink pieces are congruent. I think it's just as easy to look at this in terms of symmetry and folding and recognize that this triangle would fold right on top of that one and would be absolutely congruent. Okay? So we can use that, okay, to go, okay, well, x squared equals 9, so therefore x is plus or minus 3. So you might have something this easy where you've got a length here and a length there, and you just have to be able to set them equal to each other. This one over here would be an extension of this same theorem. So I want you to watch this one. This is gonna be an algebraic little challenge of a problem here. Okay, so let's put on here what we do know. AB is 20. So this whole thing right here is 20. BC is 16. So this whole thing here is 16. And AD is 18. So the question is, could you find the length of this with just that information? And the answer is yes, you could. So let me show you how you might wish to go about doing this. We essentially need to put a variable into this problem. I mean, if you don't want to listen to me, you can go to your dean. Okay. All right, so we actually have to put in a variable, and it doesn't really matter where we put it in, but we need to kind of put in a variable in order to kind of figure these pieces out. So why don't we start, it doesn't really matter, I'm not gonna follow this, but it doesn't really matter where we put it, I'm gonna put it right here. Now, what that means is I'm talking about this segment right here. That segment is a length x. So if that segment is a length x, how long is this? It's also x, right? Because this is an external point, this is a tangent, this is a tangent. Okay, that's that theorem we just learned. So if I'm going to call this x, I know that that's also x. Okay. All right, what? Okay, hold on, let's go back. This is our theorem that we just learned. If you have a tangent and another tangent meeting at an outside point, they will be equal in length. All right, so if this is x, and I know that this entire thing is 18, do I know something about this?
Yeah, I'd have to use 18 minus x.
Wouldn't it have to be 18 minus whatever x is? Okay, so let's put that there. 18 minus whatever that x was. All right, so if that's 18 minus x, wouldn't this be the same thing? Okay, so that's also 18 minus x. All right, this is where the algebra comes in. So if that's 18 minus x and this whole thing is 20, could we figure this piece out?
It's 20 plus x.
You're close. It's gonna have to do with 20, and it's gonna have to do with 18 minus x. Which one of these is bigger?
-2.
20. Wait, we don't have.
Okay.
X is
I know. Yeah, we gotta think. We really all have to wrap our heads around this at the same time. Which one of these things is bigger, the 20 or the 18 minus x?
20.
The 20 is the bigger piece, and we have to take away the red piece, right?
Yeah.
Now I have to take away the 18 minus x, which is an entire quantity. I see that hand, AJ. Give me 1 sec. I'm going to distribute that. So what am I going to get? 20 minus 18 plus x? So 2 plus x? AJ, what were you thinking?
Can you assume that, like, the point in the middle of the line is half of 20?
Good question. No, you cannot. We do not know that that will be the case. Okay, this problem is called a walk around problem. Because what's going to happen is I'm going to walk all the way around this circle and I'm going to get back to this pink area and I'm going to be able to add these two things together and get my answer. Okay? All right, but let's keep walking. Now, if this is 2 plus x, what is this? Boom, 2 plus x. Okay, so now we got to do this green part.
It's 14.
All right, that's going to be 16 take away the 2 plus x, but I got to distribute that. So it is 16 take away 2 take away x, which is 14 take away x. So far, so good? Okay, so if this is 14 take away x, how big is this one? Also 14 take away x. What happens when you add these together?
It's 14.
So you get 14.
That's so long.
CD.
Is that like a lot of problems?
I feel like it should have been 17.
Minus x.
Wait, why did you put 20 down there?
Wait, no.
How did you get that?
I think that's a
X
question
equals
mark.
14.
No, this piece together with this piece.
Oh.
What happens when you add those up? What happens to the x? It totally goes away.
What happens if it passes?
Look at that. That whatever that x was totally went away.
Wait.
And so we were able to figure out that that length, the whole thing, was just 14. Cooper. No, so here was the interesting part of this problem, and this is where your algebraic, you're gonna go like, because usually in algebra, we put the x's into the problem, right? We tell you what the x is. This problem, you get to decide where the x is. And guess what? If we had put the x here and walked this way around the problem, we would still get the same answer. If we had put the x here and walked around halfway that way and halfway this way, we would have still gotten the same answer. So it does not matter where you put the x. It's really just a placeholder for a number you don't know. Brad.
How'd you get the 20 on the bottom?
It's a question mark.
Oh, yeah, that's a question mark.
Sorry.
Yeah. I guess it does kind of look like a 20 now that I see.
Yeah, I wrote it too.
Oh, you guys. Oh, that's too funny. I'm sorry. Yeah, that's a question
I
mark.
was so confused.
This was a question mark. Okay.
Okay, same. I thought.
Oh boy. All right. Okay, we'll do another one of these today. You have it on your homework, so you'll have a chance to try it out on your own. Maybe I'll try it a different way when we do it again.
Is there a shorter way to do that?
Not really. Some people think it's shorter if you walk 2 directions instead of walking only 1 direction. Like, so I could try it that way. All right, find the length of the common tangent. All right, now notice in this particular case, the common tangent is this edge right here. And this edge right here is in fact labeled already with an X. Okay. So it is our common tangent. We need to find its length. Now, one of the things that's really going to be helpful, and I believe I've drawn it in this example, but it may not be drawn in your homework. It's really helpful if you remember that a tangent and a radii have a 90-degree relationship. Okay, that's going to be really helpful. So now, I want you to think about that red line that I've outlined, those 90-degree angles, and the other straight lines that we know something about. Do you see a shape that you might know something about? I see a trapezoid, right? This whole thing is a trapezoid. I think it could be a trapezoid. So don't we sometimes break trapezoids up into rectangles and triangles?
Wait,
Let's-
do you do parallelity?
Parallelity? Oh, I love that. You know what? We can because of these 90 degrees.
Oh.
Without those 90 degrees, we wouldn't be able to.
Oh.
All right, good question.
Game changer.
So what if I took this red line and I went like this? And I slid it down. I maintained my 90-degree angles.
It's magic.
Do I have, so this is an X, right? I now have a rectangle and I have a right triangle. Right? This is still a 90 degree. This is still a 90 degree. How far did I slide it down?
5.
3 units. 3
Five.
units.
Five.
3.
I slid it down 5,
Oh, you have 3 left.
but I have 3 left.
We're just
Right?
ahead of the
This
game,
will
guys,
be
so-
3 here. All right, so here's my right triangle. I've got a right triangle that looks like this. This is a 3, this is an X, and this is a 20. Do we have enough information to find the X?
Oh, yeah.
Using the Pythagorean theorem. Okay. Rebecca?
On the homework, you weren't given like the 20. You're just given the 2 sides.
That's why you walk around.
So, well, on these, this is kind of the way you want to be thinking about it is think about where could I draw a line that I do know something about? Sometimes it might be radii to radii, because you usually are given some sort of information about the radii.
It's just the 5, the 3, the 8 or the 5 would be a 3.
So once everybody has a chance to look at this problem in the homework, I'd be happy to answer that question tomorrow. Okay? So let's all give this a shot tonight. You're going to end up doing, this and solving it with Pythagorean theorem. Okay? I think you end up getting 9 and x squared is 400. So x squared is 391. So x is the square root of 391. Okay. AJ.
Isn't X the hypotenuse?
Okay, great question. Look carefully. Where's the 90 degree?
Oh.
And remember, what's across from the 90 degree is the hypotenuse. That will be a tricky thing. When you're drawing this in, try to find the important pieces. Don't just assume one or the other. Check in with yourself on that. Okie dokes. Okay, so that's the end of 9-1. Go back, make sure, you should have been able to do all of the first page, but now go back and make sure you can do the second page.